Well, here we are with the final video for Chapter 19. This is video 4, the Doppler Effect. The primary thing we want to get out of this is an understanding that as a wave source approaches, an observer will encounter waves with higher frequency, and as a wave source moves away, an observer encounters waves with a lower frequency. And we want to be able to understand that and the effects of that. So here we go. So imagine we have a bug, and this bug is sitting on a quiet lake, and he starts jiggling his legs around at regular intervals so that he sends out wave pulses away from him at regular intervals. The crests of each of those waves would move out and away from him in concentric circles because the wave speed is the same in all directions. So these circles represent wave crests of this bug tapping his foot on this lake. Now, because the bug is tapping his foot at a constant frequency, the wavelength for each of these waves is going to be the same. The same wavelength there, same wavelength there, same there. And also the frequency will be the same as the bug's bobbing frequency as well at all points around his position. But now let's suppose that our bug begins to move across the lake while still tapping his foot. So here's our bug here, and he's swimming, he's moving across this way, tapping his leg as he goes. Let's take a look at what happens to the waves as he does that. And the way we're going to do this is we're going to take a look at this kind of back in time, okay? So he ends up in this position here, but previously he was in this position here, and then he was in this position here, and then he was in this position here. So at each of these points, right, he had sent out a wave around him. And that wave was sent out in a circle around him. So when he was at that position, he was at the center of that circle. Now, since this was his final position, the wave from him there would be something like this. However, when he was at this position, right, now there's time that has passed since he's gone from here to here. So when he was at this position, he was at the center of that circle as well. But when he's at the end of his path, right, that circle then, he was at the center of it, that wave has now become something like this. When he was at this position, that wave has become something like this. When he was at this, in the first position, that wave, he was at the center of that one as well. And so what we end up seeing is a distortion of those wave crests. The wave pattern is distorted. It's no longer concentric. The center of the outer crest, right, it's made when the bug is at the center of that circle. The center of the next smaller crest was made when the bug was at the center of that circle, and so forth. The effect of this is going to be a change in frequency based on where an observer is located in relation to the bug. You see, the bug maintains the same frequency as he was before. He's tapping his foot with the same frequency he was before. So from the bug's perspective, he's sending out a constant frequency of waves. However, if you're an observer in front of the bug, you would encounter a higher frequency than if you were behind the bug. This is because each successive crest has a shorter distance to travel, so they arrive more frequently. We can see that from this diagram here when we look at wavelength. Wavelengths behind the bug are longer than the wavelengths in front of the bug. So what that means is you're going to be, if you're an observer sitting in front of the bug, then you're going to be hit with wave crests more frequently than as if you were behind the bug. So if you're an observer behind the bug, or if the bug's moving away from you, you would experience a lower frequency because it's taking a longer amount of time for those wave crests to hit you. Each crest has to travel further than the one ahead of it due to that bug's motion away from your position. This apparent change in frequency due to the motion of the source or receiver is called the Doppler effect. The greater the speed of the source, the greater will be the Doppler effect. So if the bug is moving faster, you're going to experience a greater Doppler effect. If it's moving slower, a lower Doppler effect. We can experience the Doppler effect with other types of waves other than just water. Let's take a look at sound and light in relation to the Doppler effect. So think about the times you've heard a siren go by you, whether it be a siren of a fire truck or an ambulance or maybe a train whistle as you stand on the platform. The Doppler effect causes the changing pitch of a siren. So when a fire truck approaches, the pitch sounds higher than normal because the sound wave crests arrive more frequently. When the fire truck passes and moves away, you hear a drop in pitch because the wave crests are arriving less frequently. Whenever you're driving along and you see a policeman using the radar gun, police use the Doppler effect of radar waves to measure the speeds of cars on the highway. So radar waves are they're a type of wave called the electromagnetic wave, and police bounce them off of moving cars. And then a computer built into that radar system compares the frequency of the radar with the frequency of the reflected waves, and we find the speed of the car. Bats use echolocation, right? They use the Doppler effect to tell how close the food is to them. A Doppler effect also occurs for light. So when a light source approaches, when it's moving toward an observer, there's an increase in the measured frequency. When it recedes, when it's moving away from an observer, there's a decrease in its frequency. Increasing the frequency is called blue shift, and decreasing the frequency is called red shift. We call blue shift because the increase is toward the high frequency or the blue end of the electromagnetic spectrum. The decreasing frequency we call red shift because it's referring to the low frequency or the red end of the electromagnetic spectrum. So in this picture here, a light source moving from right to left over here, this observer will see blue shift, this observer will see red shift. So a question to think about then is, when a source moves toward you, do you measure an increase or decrease in wave speed? The answer is neither. The frequency of a wave undergoes a change, not the wave speed. So if you think about this in relation to the light, right? The Doppler shift in light. Light doesn't change speed at all, right? But we're getting a change in frequency depending upon where you're observing that light. The Doppler effect also allows us to talk about what are called bow waves. A bow wave occurs when a wave source moves faster than the waves it produces. It's very characteristic of boats on a water or even ducks swimming across water. You get this wave pattern behind the boat, right? Because this boat is moving faster than the waves that it's producing. Let's think about our bug swimming across the water, okay? When the speed of the source in a medium is as great as the speed of the waves it produces, this interesting thing called bow waves happens. The waves begin by piling up. If the bug swims as fast as the wave speed, it'll keep up with that wave crest it produces. The bug moves right along with the leading edge of the waves it produces. The same thing happens when aircraft travels at the speed of sound. The overlapping wave crests disrupt the flow of air over the wings of the airplane, so it's harder to control the plane when it's flying close to the speed of sound. Our bug here would experience a similar effect of being harder to control at this speed, because you can think of these wave crests as getting bigger and bigger. It's going to be harder and harder for that bug to stay at that speed, right? It's going to be harder and harder to control himself as he swims at the same speed as the waves he's producing. However, when our airplane, right, is traveling right at the speed of sound, and it's got this hard to control because it's riding all of these wave crests, but if it goes a little bit faster, the plane then is traveling faster than sound. It's traveling at supersonic speed. So a supersonic airplane will fly into smooth, undisturbed air because no sound wave can propagate out the front of it. And this is similar to our bug here, right? Our bug, if he speeds up a little bit more, so he's moving faster than the waves he's producing, then he's always going into an area out here where the water's nice and smooth and unrippled. So when the bug is swimming faster than the wave speed, it outruns the wave crests that it produces. And the crests then overlap at their edges, and we get this pattern made by these overlapping crests. resulting in a bow wave that appears to be dragging behind the bug. So a familiar wave generated by boats on the water is produced by the overlapping of the many circular wave crests behind the boat. So here we can see the wave patterns made by a bug swimming at successively greater speeds. And we see that the overlapping at the edges occurs only when the source travels faster than the wave speed. We can see that that bow wave there trails behind the bug whenever he's moving faster than the waves he produces. Now, there's a difference between a bow wave and a shock wave, right? We got to remember the bow wave is just that wave that's produced right at the front. Then there's something that's called a shock wave. A shock wave occurs when an object moves faster than the speed of sound. Okay, so a speedboat moving through the water generates a two-dimensional bow wave. Okay, a supersonic aircraft will similarly create a shock wave. A shock wave is a three-dimensional wave that consists of overlapping spheres that form a cone. Okay, so while the bow wave is two-dimensional on the surface of the water, a shock wave is three-dimensional through the air. Okay, so this conical shock wave that's generated by a supersonic airplane spreads until it reaches the ground. So if you're on the edge of the water or something, a bow wave, right, of a speedboat that passes by can splash you. In a sense, you can say that you're almost hit by a water boom. In the same way, this conical shell of compressed air sweeps behind this supersonic aircraft. The sharp crack heard when the shock wave that sweeps behind a supersonic aircraft reaches the listeners on the ground is called a sonic boom. Now, you're never going to hear a sonic boom from an airplane that's traveling under the speed of sound. The sound wave crests reach our ears at one at a time, and we perceive that as a continuous tone. Only when the craft moves faster than the sound do the crests overlap, and we as a listener encounter that single burst. Ears cannot distinguish between the high pressure from an explosion and the pressure from many overlapping wave crests. Because it's this boom noise that's heard by an observer on the ground as the waves pass by that person, it leads to a common misconception that sonic booms are produced only at the moment that the aircraft surpasses the speed of sound. That's not true. In fact, a shock wave and its resulting sonic boom are swept continuously behind an aircraft traveling faster than sound. As an example, we look at this situation here where we have the airplane that's traveling faster than sound. It's created a shock wave, and we've got listener A, B, and C. The shock wave's not yet encountered listener C, but is now encountering listener B and has already passed listener A. So listener A has heard the sonic boom, listener B is hearing it now, and listener C has yet to hear it. You can even see the shock wave behind a plane as it's traveling past you faster than sound, as it condenses the air right near it, right? So from the perspective of a pilot from the plane, this little cloud is always there, but it only shows up as it's passing an observer that is outside the plane. You don't need an airplane either to experience a sonic boom. A supersonic bullet passing overhead produces a crack, which is a small sonic boom. If a person cracks a bullwhip, the cracking sound is actually a sonic boom produced by the tip of that whip. You can even go and grab a towel right now, wind up that towel and snap a towel, and at the end of it can exceed the speed of sound and produce a little tiny sonic boom. When you snap a towel, that's what you're doing. You're creating a little sonic boom. So the bullet, the whip, and the towel are not in themselves sound sources, though. When they travel at supersonic speeds, sound is generated as waves of air at the sides of those moving objects. Well, that'll do it for our coverage of vibrations and waves. Make sure that you go back into the previous videos and make sure you're getting notes taken and you're understanding these concepts. We'll talk about them a little bit in class and see some demonstrations and do some activities to help sink them into your brain. See you in class.